Hello and welcome to another SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Earlier this week, we announced a partnership with Louisiana State University and Mississippi State University to help their students design the science program for a lunar-based camera called Lcam1, designed by AstronetX. Dr. Tabetha Boyajian from Louisiana State University leads the science team, and she has joined me today to discuss the new project. So thank you and for joining us, and welcome, Tabetha.
Thanks, Beth. Good to be here.
I'd also like to welcome all of our viewers from around the world. Please let us know where you are watching from, and we will give you a shout out. And just as a quick note and a reminder, SETI Live is an outreach project of the SETI Institute, which is a 501c3 nonprofit dedicated to the search for and understanding of life beyond Earth. So if you would like to support this outreach program, remember that your Facebook stars, your YouTube super chats, and your Twitch bits all help us contribute to bringing you amazing science stories. All right, Tabetha, I am so excited to have you here. I can't even begin to tell you. All right, what is Lcam1? Can you give us a brief interview of this particular project?
Yeah, Lcam1 stands for Lunar Camera, and this is a camera that a mission that's designed to be based on the moon, particularly the far side of the moon is what our study involved. And as opposed to all the other science investigations that are going up there in the next couple of years, this one is going to be looking up at the stars and not down at the dirt.
So why the moon? How does the view differ?
Well, when you launch something, say so a satellite or something like that into space, to get really good data, you need stability. And the moon provides us a very stable surface for pointing and observing whatever star field that you're looking at. Telescopes that are based here on Earth have to look through the atmosphere, and that's basically what makes our stars twinkle, and that also makes your data very hard to calibrate and look for, very small sensitive signals and such like that. And so since the moon doesn't have an atmosphere, we have that advantage as well as the stable ground that you have a telescope to put on.
So what are the science goals for this mission?
Right now we have a few different science goals. The first one is a science program that's built on looking at bright stars, mainly that host exoplanets, so stars or planets going around stars other than our sun. And we're going to be looking at these stars, monitoring them for 2 weeks at a time. It's basically when you have your telescope stationed on the moon, you'll observe for a lunar day, what we say. So it takes a lunar day is actually 14 days long. And then the night is 14 days long, Earth days.
Yeah.
14 and 14. And that's, what takes the moon to orbit the Earth. And so we'll have 2 weeks of observations that we can get from these astronomical sources. So the stars that we're looking at that are hosting exoplanets, we're looking for what's called a transit. And so this is when you monitor the star's brightness over time, and you watch for the chance alignment of a planet in orbit around that star and it crossing between us and the star itself. It casts a little bit of a shadow on the star, and that is seen as a little drop in the light curve.
And then there's a planetary defense aspect to this, correct?
Yeah, that's right. That's the other side of the science program, is looking at main belt and near Earth asteroids. So we're looking at several dozen of those to refine their orbits and also characterize their shapes and their motions and their binarity and that sort of thing, to learn everything that we can about those really interesting objects.
So how did you and your students become involved in this project?
We got together, I guess it was about a year ago now. We started talking about this, and a colleague of mine, John Morse from AstronetX, who was interested in developing a science program for this lunar camera. And so he came to us and he said, well, listen, we want to develop this science program, but I do believe that, student involvement is definitely something that, we want to, focus on and make sure that it is an integral part of the mission design and planning from the very beginning. So a lot of times when you have students working on things, they're working, with the data. So TESS telescope is flying up and data gets deposited in the archive. And then you have students, they go get the data and they, work with the data and, that sort of thing, which is fine. But this gives a different kind of perspective on how the science and the operations and everything kind of gets put together. From developing the mission from scratch, like what kind of questions you need to ask to make things happen, like what kind of science you want to do. You have to develop an observing program that's specifically tailored to answer those questions. And so these students were all exposed to this type of process during the time since last year. And I think that's been truly invaluable to, their experience in science research.
I want to ask you more about the students, but first I want to give some shout outs here. We're getting some locations. So I want to say hi to people watching from Australia, the Azores, Montreal, Canada, Norway, California, Michigan, from Mississippi State University, Saudi Arabia, Minnesota, Portugal, and hi, Frank, I see you out there. Our own Frank Marchis is also a part of this project, so he's watching from the background. So if you do have questions for Frank on the planetary defense side of things, feel free and I'll make him answer them either now or later. Also, one more shout out. I want to say thank you to Freddie on Facebook for the stars. So thank you for your donation. Okay, Tabetha, is one of the goals here then, because the students are working on this project from the beginning, essentially, to have some of them work on it all the way through to collecting data and doing data analysis once that's up and running?
I mean, I see students are quite, they migrate on through different institutions and have different kind of things that they, transitions that they go throughout their career. So I don't imagine that someone will primarily work, a student will primarily work from their undergraduate, all the way through to the missions flying phase. It could happen. But this gives them kind of the exposure to, how these processes work in general. So they can kind of, the next project they're working on, they can, hit the ground running, so to speak. And, know all the nomenclature and be able to, share their, simulations and results with a broad range of other astronomers that have different backgrounds and that sort of thing. And so they had experience doing various things. That said, the team as it is now is not necessarily kicked out. Once they leave or graduate or something like that, they definitely remain. We have students that we're working with us over the summer through an REU program that still do attend group meetings, and they're still on our Slack and such like that. So they're definitely very interested in seeing the progress and stuff as things progress. But their roles in it aren't as integral as they were, when they were previously, like, that's what they were doing 40 hours a week.
So will you walk us a little bit through the design process, the science program design process? Where did you start? Where did the students have to start?
Well, it came from a couple of different angles, and then a few different angles, and then we kind of met together and tried to work it all through. So the first aspect that you need to think about is your instrument, your camera, your telescope, and what kind of data that you're going to get. So say you have a telescope that has, this one is, you can think of it, if you're familiar with the TESS mission, it's a scaled down version of a TESS telescope. So it's a small telescope, about 5-centimeter aperture. And we had the specs from the manufacturer of the camera. And so building what's called an exposure time calculator was something that was very important to estimate how long can you look at a given star, and are you going to say saturate the camera, or how much how is your data quality going to depend on your exposure time, right? So you have a delicate balance there on, if you're looking at a very, very bright source, you don't want to have a 10-minute exposure time because the data is going to be completely unusable at that point.
Right.
And so you want to be able to also get up enough signal that you do have the sensitivity to detect something that's a planet. So, sub% precision on our observations. And so characterizing the instrument and finding out what the optimal tunings were for these properties was a big role that they played in. And especially if you look at the two different science cases, if you're looking at bright stars that host planets, and then if you're looking at asteroids and planetary defense, they're two very different regimes of stuff that you can look at in the sky. One is very bright and one is very faint. And so we kind of had to, optimize the two and make things work for the both of these consistently. So once these were together, we kind of, revisited the actual camera and where the camera was pointing, right? Like, what does the sky look like when you look, or when you're observing from the moon, right? Like when you have the moon rotating once every 30 days. So you have a 14 Earth day observation window, right? And say your camera is placed on kind of near the South Pole on the far side of the moon. If you point up a little bit from the horizon, right? And just, let time go on, how do these stars move through your camera's field of view, right? Like, how big is your camera's field of view? What are the pixel sizes look like, depending on, how are these stars going to track across your camera as the moon rotates? And so they worked out all these positions, what the field looks like, what objects were going to be in the sky at different times during the entire year span of 2024, and putting together target lists and kind of slew sequences to, match up, optimize the observing plan. Another thing that was necessary is, you're not just looking at, your science star itself. That was interesting. You want to have a handful of like calibration stars, just make sure everything is, behaving normally. And so, selecting all of these and how that would fit into your observing plan. And then lastly, like, what's your data going to look like in the end? We have pretty intensive demands for data volume, like how much data we want to send back to Earth. We're talking about really big pictures taken, every few seconds, which is a lot of data and definitely can't handle that. And so being able to take basically from the data that is being taken, take what we need, right, and send that back to Earth. And so what was the optimal, like, kind of snippets or postage stamps, as we call it, that we would want to send back to Earth that will still have all the data, all the information that we want.
So were they running simulations to analyze, to figure out some of these, the way this would work?
Yeah, there were a number of simulations that were run. The exposure time calculator was something that was built from scratch with the instrument specs and various other things. So it was customized specifically for this instrument. The kind of the field of view simulation was done with a software called Stellarium,
Yes.
which is a free open source software where you can actually place yourself on any planetary body and look at the accurate representation of what the sky will look like at any time of year, and you can put in your own telescope configuration settings and such like that. And so that was kind of the base of the visualization of learning, okay, well, what are we actually going to look at? Like, what are these, what are these things, putting the constellations, labeling them, and say, oh, okay, everything's upside down in the southern hemisphere of the moon, just like the southern hemisphere of of Earth. I want to say upside down to a northern hemisphere person. And so it was very much a learning experience for all of us, including me. And so the simulations in Stellarium was used also to find kind of the coordinates of the corners of our field of view at a patch of sky at a given point of time. And so once those were derived, Frank Marchi and his group, he had a student from the University of Puerto Rico that was working on cross-matching these coordinates within that postage stamp from Stellarium with the locations of near Earth asteroids and main belt asteroids that would fall within that field of view during that time of year, 5 years from now, whatever that was. Likewise, it was also cross-matched with the NASA Exoplanet Archive and those catalogs that have catalogs of all the known, planetary systems around these bright stars.
All right. I want to give a few shout outs, and then I'm going to take some questions from the audience. So if you have questions for Tabetha, please let us know, and those will get passed on to me. And but first, really quickly, some shout outs. We have people watching from San Francisco Bay Area, so welcome. Utah, Connecticut, Vermont, Costa Rica, and also a big thank you to Gregorio on Facebook for sending stars as well. So thank you so much. And Tabetha and Angel Tanner says hi. So apparently she
from Mississippi State.
So there you go.
He is also a collaborator on this project.
Yes. All right. Fantastic. So it's nice that they're all coming out to support you. Very nice. Okay, so we've talked about sort of what the goals are of this program. We've talked about how the students worked on it. So now I want to ask you sort of just sort of the basics here. What's the timetable on this? When's it launching? Where's it landing? What's the physical process of all of this that's going to happen now?
So we are targeting to launch in, say, 2024, 2025. The study that we performed last summer, which this press release is all about, was based on a landing site on the far side of the moon, down near the South Pole, not all the way. It was 75 degrees south, so close to the lunar South Pole, in a spot called the Schrodinger Basin. That might not end up being where we will end up landing in the long run, because this is still several years away. But that's one of the things that we've learned so far in the mission planning that we've done. There's been some things that have changed, and we've learned to be smart about how we build our programs, to build target lists and that sort of thing. And so we're able to like quickly go in and say, oh, we're not landing there, we're landing here, and then just rerun things and then have the results in hand without that much of a headache. And so that was definitely has been a valuable lesson to teach all of us on that. And so so timeline is in just a few years. The first landers are headed up to the moon in the next few months, I believe. And so it's a really exciting time for, lunar exploration. Yes, I know, right?
Fingers crossed.
Don't get in the way of anything.
NASA timelines have a tendency to slip a little bit, so every so often.
Right.
Well, and that is why I asked about the current timetable, because I do know that these things, space is hard, everybody. Space is hard. So some questions from the audience coming in, and also hi to viewers from France and Seattle, Washington. will the regolith be a challenge to the telescope? And have you guys considered if the regolith is going to be an issue for putting that lander down?
Our engineers believe that they have that under control. That's all I personally know about about it. But China's had 3 successful landers in the past close to 10 years or so. And it doesn't seem like that has been an issue for that for their missions. I could be mistaken, but our engineers believe they have the whole lunar dust thing under control. And there's actually some interesting things that you can learn about with the dust. So even they could be, it could present a problem, but it could also be very interesting as well. And so we're definitely keeping an open mind to that.
Another viewer question. Is the far side of the moon going to cause any issues in updating programming for the camera due to the line of sight and communication issues?
Right. So the way we planned it out currently is that we're going to have a data downlink every 24 hours, so every Earth day. And I mean, so you won't be able to continuously talk to your telescope systems. You'll be able to check in every 24 hours to get that data download, and maybe upload your programming sequence. But definitely you have that far side, doesn't have the capability to directly speak to Earth. Like you have an orbiter, right, where you're going to have communications relayed and then back, so you can get your signals back to Earth from the far side. You can't directly go from
right. It's like I said, space is hard and can get complicated. I know that a lot of these same things are considerations for the Artemis missions, which also would like to land closer to the South Pole and potentially on the far side, building a base there. So people are working on these problems, and hopefully
the far side for people, I think, is quite risky, because people have to stay alive and stuff like that. We're worth a lot more money than a little telescope. So definitely would be more concerned if it was a person that you'd be putting on the far side of the moon than an instrument. But it is super interesting because you have a kind of view from that side that you can't get from Earth at all. Right. Earth not only has an atmosphere, but we go through these day-night cycles because we rotate once a day. And so we'll be able to see things in the Earth daytime sky that we can't, that you can't see from Earth. And the continuous 2-week observation window definitely is an advantage as well.
All right, we're getting close to the end of our time. Is there anything about this mission I haven't asked you or you haven't gotten a chance to cover that you would like to bring up?
No, I can't think of anything right now.
All right, then I have one completely unrelated question, because I know some people in our audience are probably thinking it, and I'm going to go ahead and just throw it out there. How has your life as a scientist changed with the discovery of Boyajian's star?
How has my life changed? That's an interesting way of putting it. Well, I have somewhat of a love-hate relationship with that star. It's insanely interesting, right? Because it keeps throwing us curveballs and we can't really figure it out. Just in case some of the audience doesn't know what we're talking about. There's a very weird star that we discovered probably about 5 years ago now. And it has these very crazy brightness fluctuations. And all natural scenarios that we can think of have kind of been ruled out. And so there is a alternative idea that it could be some sort of alien megastructure that was orbiting the star and causing these light fluctuations. Anyway, I believe that's been ruled out as well. So we're still really trying to work on a model that will, work with all the data that we've collected so far. We've still yet to find any periodicity, which makes it very frustrating. But part of my time does still focus on work with that star, surprisingly.
It hasn't gone away for you, huh?
I think it's going to be like a career project. Yeah, it goes back to that love-hate relationship. But for a while, it was an attention hog, and it was. I think personally, it was hard to manage my, because I did other science too, right? But that kind of like took over everything else.
I can imagine.
Nothing
Yeah.
else was important at that point. But I mean, I think at this point I found a happy balance, and I'm actually super excited that it's, the discovery of that one is kind of, spawned that new area of research, but kind of just a different way of looking at things. Instead of, just having algorithms trained to find, periodic things, we're now like, looking for like stuff that's weird and doesn't look like anything else, which is really cool. I think, because now we have, we're in this, era of big data, and we can make these kind of discoveries now with the computing power and everything that we have available to us. And, this thing, itself was discovered by citizen science. And, I always wonder, if that wasn't developed, I guess maybe eventually it would have been discovered, but the signal itself was huge, but it was nothing that we were looking for. So you never know.
I feel like Boyajian's star was sort of where the line starts to shift from, oh, here's an exoplanet, oh, here's an exoplanet, oh, here's an exoplanet, to, yeah, we know there's exoplanets, here's something weird. And so now, like, the news stories are no longer here's an exoplanet, it's here's this weird exoplanet, here's this strange exoplanet, here's this thing we didn't expect to find. And then the exoplanet discoveries are more from the big data side, where it's like, here's 400 new exoplanets we found because we ran our machine learning and it worked.
Yeah.
So I feel like your star kind of shifted the conversation a little.
Okay. Well, it makes things fancier, shinier. Okay. I like that. You do that.
All right. Well, Tabetha, thank you so much for joining us today. And thank you for answering questions and hanging out. And I really appreciate that you were here.
Thanks for having me. And thanks to all of you online. And hello to all of you online for coming and hanging out with us for this little bit. It was fun.
So once again, we are a nonprofit. Thank you for your donations. Your stars today are much appreciated. And also things are available over on YouTube and Twitch if you want to give to us, or if you just want to go to our website, you can go to SETI.org and find out more information there. And also sign up for our newsletter so that you get announcements of some of our special events. There are a few things we don't publicize very widely, and you probably want to get on the mailing list for those. Coming up next week, we will return with SETI Live with the director of our SETI Artist in Residence program, Bettina Forget, and she will be here with the former director of our program, artist Charles Lindsay. So please join us again next Thursday, January 27th. It will be at 2:30 p.m. Pacific, which is our normal time, 5:30 p.m. Eastern, and 20:30 UTC. So I have to use converters usually for those things, but there you go. So I hope to see everybody here next week. And once again, thank you, Tabetha, for being here.